Real quickly, I forgot to mention in the last video that the derivative of e to the x being e to the x is actually number 9 on your formula sheet. So if you look at it right here, we have it as e to the u. Again, the u part is just because of something we're going to learn in section 3.7. But so you can think of it as e to the x is e to the x, and then x, the derivative of x prime, would be 1. So this part would go away, and it'd just be e to the x. So that's rule number 9. All right, so now we want to head into a very quick topic, which is higher order derivatives. So not only can you take a first derivative, where the derivative is the slope of the tangent line, but you can take the derivative of the derivative. So, and that's because taking a derivative itself is a mathematical operation. So we can do this over and over and over. We can, just like we can multiply over and over, subtract over and over, we can actually take the derivative, differentiation, over and over and over. And that mathematical operator, just as a reminder, is the d over dx operator. Technically, it's also the prime, if you want to think of it that way, but the prime is just not very useful for this type of application. So the mathematical operator itself is d over dx of whatever the function is, right? So, but this is the operator itself. And what that's telling us to do is take the derivative with respect to x of this function. Okay, so we're going to find the derivative of f of x. Well, okay, that's a lot. So here's what we're going to do. We're going to start by finding the derivative. The first derivative is what it's called, right? Which is all the derivatives we've taken so far are the first derivative. Okay, so that is d over dx of f of x. In other words, it's f prime of x. This is Bernoulli notation. This is Leibniz notation. Or heck, if you want Euler notation, dx of f of x. Right, those are all the notations. Or, I shouldn't say all. Those are the three big notations that we learn. All right, so take the derivative with respect to x of f of x. Take f prime of x, which is the derivative with respect to x of f of x. Well, this is not difficult because it's a polynomial, so I would just bring the 4 down, right? This is a power rule, so 3 times 4 is 12, x to the third plus 2, right? This is x to the 1, when you bring the 1 down, 1 times 2 is 2, and then it becomes x to the 0, which is constant. And the derivative of a constant, 1, is 0, so that's why there's nothing else over there. So this is the first derivative. Now they want the derivative of the derivative, so they want the second derivative. So that would be d over, here's second derivative. Okay. So if I think of this first derivative as dy over dx, right, the derivative of the y function, which was right here, y equals f of x, with respect to x, then I want the second derivative. I want the d over dx of d over dx of f of x, right? So as confusing as that is, so I want the derivative of the derivative. So I want to take d over dx of the 12x cubed plus 2 that I already found, which is, let's think, 3 comes down, 3 times 12 is 36, so it's 36x squared, and the derivative of 2, because 2 is constant, is 0. So right there. This is also known as f double prime of x. Right? So 1 prime is the first derivative, 2 primes is the second derivative. All right, now for the next part, they want us to take the derivative of that derivative of the derivative that we found. Right? So now I want the third derivative. All right, at this point, I'm not going to even bother with Leibniz notation anymore. Just because it gets really annoying. So I will actually continue with Newton and Bernoulli notation, which is the prime. So I want the third derivative of x. Now there's two ways you can write that. You can do triple prime. Triple prime's weird because it's kind of the last one that we will do primes sometimes, but we also can use the other notation, which is you put a parentheses around that power 3. So it's f third derivative of x. So you either use parentheses or you use primes. But after 3 primes, we never use primes anymore. So 3 is kind of the end of it. And honestly, a lot of times we don't do triple prime. We'll do the 3 parentheses. But 4 and 5 and so on, we definitely use parentheses. All right, and that would be, we'll bring the 2 down in front. 36 times 2 is 72x. And just in case you're wondering, they didn't ask for this, but the fourth derivative would be, and at this point we definitely put the 4 in parentheses, and it would be 72, right? Because, and then the fifth derivative would be 0, in case you're interested. So the third derivative can be primes or parentheses, but after that point we always use parentheses, and that's what we have right here. So the higher order derivatives, the most common, the one we will use way more often than anything else, well, we'll use the first derivative the most often. And then next we'll use the second derivative the second most often. So the second derivative is f double prime of x, which is also, and we're showing you the notation down here at the bottom of the page, it's also d squared f over dx squared. So this would be d squared f over dx squared. That's how that works. Right, that's the second derivative. Okay, so then for integers n greater than 2, the nth derivative is f, and then see the n in parentheses, that indicates that you're taking the nth derivative. And I lied to you a little bit earlier. The Leibniz notation isn't terrible, because what it would be is dn of f over dx to the n. That's how it would work. So for example, if I just backed up right here, for this third derivative, that would be, this would be d cubed f over dx cubed. What you're saying is I took the derivative 3 times and with respect to x every single time. So it's dx cubed. Right? Or if I did, well, this one we could say is d squared f. Take the derivative twice of the same function, and I used x every time as my variable. Now you might be thinking, well, why is that useful? Well, in Calculus 3, it will not always be x. So in Calculus 3, we'll actually do derivatives with respect to x one time, then y the next time, and so this notation actually is way more useful for the prime than the prime notation in Calc 3 in particular, in multivariable calculus. So there you have it. But for Calc 1, we tend to use them both a lot, especially for first derivatives, we'll write them both all the time, and second derivatives. So, and then for Calc 4, it just depends on what we're doing, or Calc 3 and Calc 4. So this is what we did. So this is the answer here, that's the answer there, this was the answer, sorry, this was the answer right here. I forgot to circle my answers, and this right here. All right, so higher order derivatives are when you take the derivative so many times, and in Calc 3 we'll go past this, but for Calc 1 and Calc 2 this is kind of the extent of what we will do. So first derivative, second derivative, third derivative, and everything's always with respect to the variable in the function. More or less. There's a caveat to that later in this chapter. And again, for Leibniz notation is a little bit weirder for students to start with. So this is Leibniz notation, named after one of the 2 people that invented calculus, Leibniz, who was living in the German court. So he was kind of an intellectual, German intellectual in the 1700s, late 1600s. So Leibniz wrote this way, which is d squared f over dx squared. So d's 2f, right, d squared f over dx squared. Right, you're basically saying I'm taking the derivative twice with respect to f, and both times I took it with the x variable.